As modern systems become progressively more complex, the task of coordinating development efforts becomes more difficult. Part of the challenge is that the engineering organization deals with a diverse, multi-vendor toolset, and system data lives in many places and formats. This allows inconsistencies and gaps to arise in the organization's understanding of the product. Model-based engineering, MBE, addresses this by creating a single, unified model of the system, extending over all the tools and data repositories. Syndeia from Intercax is a platform for creating a graph, a fine-grained network connecting elements in different models in different tools. In this video, we will apply MBE and Syndeia to modeling a product from the Internet of Things domain, a network component that registers the presence of employee RFID name tags and directs audible pages accordingly. We will model both the project and the product using a core architecture in IBM Rational Rhapsody and a variety of other software tools connected to Rhapsody by Syndeia. We have divided this demonstration into 3 parts: building, using, and visualizing the graph. We start by populating the SysML model with project requirements from a Doors NG repository and product requirements from a JAMA repository. Opening the Syndeia dashboard, we find the project requirements in Doors and drag the top-level requirements collection, project requirements spec, into an empty package in our starting SysML model in Rhapsody. Similarly, we use our link to a JAMA repository, find the LP product spec, and drag it into a different package. The 3-level requirements hierarchy is preserved. This is not a one-time export-import action. As we will see later, the SysML, Doors, and JAMA requirements remain linked. After the requirements have been brought into the SysML model, we continue to develop the architecture of first the project, then the product in Rhapsody. On the project side, we can express the process as a hierarchy of activities, with 4 phases at the top level. Phase 1 is further decomposed into lower-level activities, and so forth. Next, we model the organization and team members that will conduct this project. Based on this, we can create a work breakdown structure, or WBS. A critical step is to link these elements in the SysML model. As shown in this diagram for the first phase, project activities satisfy project requirements and are allocated to WBS tasks. These tasks reference the organizations assigned to carry them out. As the project proceeds, we architect the product in another part of the SysML model. We specify the hardware and software structure in SysML, which we use to seed models and external tools. The hardware block structure, for example, can be transformed into a PLM bill of materials, and the connectivity between software modules, as here, can be used to create a Simulink block structure as a foundation for simulation. In the same way, the work breakdown structure hierarchy can be used to create a mirror structure of tasks in a Jira issue tracking repository for project management. In each case, the elements in Rhapsody and the other tools maintain a persistent connection, which enables us to use the graph. There are different ways to use the connections. As a first example, we can use them directly to access the external elements from the SysML model. The front enclosure and the hardware structure is linked to a CAD model in Siemens NX. We right-click the SysML element, choose Open Connected Element, and launch NX to view or even edit the CAD file. In the same way, we can open the related JIRA issue from a WBS task block. Other connections allow comparison and synchronization between elements. In Rhapsody, we can edit a project requirement specification that was originally brought in from Doors NG. We modified the text by adding an additional approval. Now, using Syndeia, we request a comparison between the Rhapsody and Doors version of the requirement. A difference table is generated, highlighting the text, which is the differentiator. The same connection allows us to update the requirements in either direction, assuming we have the necessary write privileges. Pushing the original Doors text back to Rhapsody, we see the changed text has now disappeared from the requirements diagram. Beyond these features, there are benefits from just being able to trace the connections across the graph, both intermodel connections between tools and intramodel connections inside a single tool. In Syndeia 3.0, we introduced some new visualization capabilities. We can view all the intermodel connections in a chord plot, where the peripheral nodes in different colors represent Rhapsody, Team Center, Doors NG, Simulink, NX, GitHub, Jira, Jama, and MySQL. A search box lets us look for specific nodes and connections. We can also launch views of the graph from a specific element. Here we invoke Syndeia from the WBS Review task block in Rhapsody. The new view shows the connections to the nearest neighbors, the project management organization, a JIRA issue, and a project activity. Expanding project management further, we see the details of the organization and its connections to the MySQL table, where team member information is stored. Expanding the activity, it connects to a Rhapsody project requirement, in turn connected to a Doors NG requirement. A chain of relationships extending over 4 different software tools has been revealed. As the total system model becomes larger, this kind of manual searching is not enough. Using a prototype of Syndeia 3.1 to be released early in 2017, we export the graph to a Neo4j graph database with powerful query tools. Using the SQL-like query language, Cipher, we ask the database first for all SysML blocks connected to JIRA issues. We see the diagrams or a text list for the results. Now we ask for all SysML blocks that satisfy a specific JAMA requirement, appearance. The list shows two, the front and back external casings. We can easily extend the query to show all blocks affected by the appearance requirement, directly or indirectly, which includes the hardware subsystem, the complete product, and the WBS task for external design. Again, we can toggle between diagram and text. Reversing the query, we ask for all the requirements that impact the front casing part, directly or indirectly. These include dimensions, mounting, and weight, as well as appearance. The use of modern graph databases holds enormous potential for the future of model-based engineering. Contact Intercax to learn more.